Okay, yeah, thank you, Oleg. Yeah, so let me first thank you for inviting me, and Dr. Yang also invited me to this workshop to present my work. So yes, as you can see, the title of today's talk will be modeling the elastoplastic behavior of solid materials. So we kind of focus on for a new method we have developed in last couple of years. So which is called the lattice particle method. So before getting into the meat of this presentation, I'd like to thank my former PhD advisor, Dr. Univ, who is still at Arizona State. So and also my former colleague, Hailong Chen, on this work. So this talk will mainly focus on like from the engineering perspective. So different from the previous talk. So I will more focus on engineering-based application without like further rigorous mathematical improvement of this method. So with that being said, so let's first look at the outline of this presentation. So I will briefly give some background of this work and why we motivated to do this type of work here. So with that, and then starting talking about modeling the elastoplastic deformation of solid materials using a new type of method. So talk about general formulation of this method and also application of this method. First, for sure, we want to look at linear elastic material behavior, whether we can model that very basic material behavior. So after that, going to the main content of this talk is the isotropic plasticity behavior. So since again, this is a reformulation of the conventional continuum mechanics theory. So, and then we want to extend this method to look at the plastic deformation of materials. Then how can we formulate equivalent, say if we use J2, the von Mises failure, von Mises yielding criteria in the conventional continuum mechanics, then how can we get the equivalent J2 plasticity theory for this specific LPM method? So we are specifically talking about the yield function and the flow rule and then strain hardening, how we handle those three different pieces in this new LPM method. So at last, I will also briefly mention some ongoing work along this direction. Okay, so as we all know, most of engineering problems are described using partial differential equations. So, and also such as like the continuum mechanics theory. So which is shown here using, this is the equations of motion used in the classical continuum mechanics theory. So so for all the notations, that's good. I mean, during Dr. Han's presentation, he already mentioned a lot of notation would be used in engineering problems. So I think those notations can be easily applied to here. So the rho denotes the density of the material and the U denotes the displacement vector. And also the sigma is the stress, and the B here is kind of the body force. So we have basically is a stress divergence term here. So for this problem, without any spatial discontinuity, I mean here is like such as some material interface, like you may have discontinuity at the interface you have if you have two different materials. And also that is kind of a weak discontinuity. And also you can have a very strong discontinuity. That is you have a crack, right? You have a failure, you have a crack in your material domain. So for those type of problems, finding element method, I mean, basically the continuum mechanics theory will have issue. So at that discontinuity, basically the partial differential equation will break down, okay? So you will have singularity as such as at the crack tip, then which will give you infinite stress. And then basically you cannot, in terms of numerical, you cannot solve this problem. So as alternatives, so there are different methods to handle this problem. So LPM, which is referred here as the lattice particle method, which is the method I'm going to talk here. So this method reformulates the governing equations or the equations of motion rather than using the partial differential equations, as we already know that is used in the conventional continuum mechanics theory. So here we use a different, we call it integral differential equation. So the integral refers to the spatial differentiation. So we don't take spatial differentiation, we just do the spatial integral. The differentiation, we still have the time differentiation, which is the same as in the classical continuum mechanics. Okay.
That's the illustration.
So if we present it in terms of the equations of motion, which is shown here, as you can see, the difference between these two equations is the basically the stress divergence term in the classical continuum mechanics was replaced using the integral term here. So by doing this, since we don't require any, first, since we don't have any spatial differentiation in this new type of equations, then we don't require any explicitly any continuity of the field, such as the displacement field or the temperature field you're going to solve for. So that will avoid the issue at the crack tip or at any discontinuity tip. Those are stress singularity issue. There are some other advantages of this method. So since here our focus is to look at the modeling the failure behavior of solid materials, then this method for sure, first, we don't use the partial differential equation to describe the physics of the material. Then we inherently avoided that kind of spatial discontinuity related issue in that theory. And also in terms of modeling fracture behavior, so we want to have some failure criteria. So as May already discussed in the previous presentations on the similar topic. So in this method, we kind of can easily model the fracture behavior just by breaking the bonds connecting different lattice sites or material points. Okay, so another set of advantages of using this method is for the anisotropic materials modeling. So which I'm not going to touch here, but that is just another set of advantages of using this method. So this talk will mainly focus on developing elastoplastic modeling capability of this method. So even though our goal is to look at the material failure, but before we can look at the failure, we need to have such as like if we want to look at the brittle failure, we may need to be able to model elasticity. And then if we want to look at the ductile failure, then we need to have an elastoplastic modeling capability of this method before we look at the failure problem here. Okay, so that is some basic background about this method. So let's look at the general formulation of this method. So as the name, as you can refer from the names, it's called lattice particle method. So basically here we have a material domain. Okay, the material domain is still continuous. Okay. And then we just discretize the material domain rather than like if you choose a finite element method, right? You need to mesh the material domain or the physical domain. Here we not use that kind of technique, but we just discretize the material domain, whatever material domain you may have, but you can choose different lattice structures to discretize the domain. So for 2D, we use the two lattice structures. One is the triangular lattice, and then another is the square lattice. So for 3D, we basically so far we look at is the cubic lattice family. That is the simple cubic and also the body centered and the face centered. So for modeling isotropic material behavior, these basically are the same. They can yield the same kind of, for sure, the same solution. And then in terms of implementation, they are the same. But for the anisotropic material behavior, these different lattice will be more suitable for look at the solids, which may really have the underlying lattice is maybe really is a simple cubic. Like let's say if you look at a metal material, like you have a real lattice structure for the atoms, right, to pack in certain pattern. So if the material have a body-centered cubic, then it may prefer to choose the BCC lattice, the body center lattice, to discretize your material such that kind of you mimic the real molecular packing at the very lower scale. So if you have a FCC lattice, then you kind of use that to look at the material of that lattice type. Okay, so with the lattice structure given, then the next thing is we want to identify the unit cell for each type of neighbor. So you can include the interaction, like you have a reference particle, it can interact to the particle up to certain distance, okay? So here I just listed two type of interactions. The first is interact with the first nearest neighbor. Then based on that, since this is a regular configuration, then you can easily identify the unit cell for the interaction of that reference particle with its first nearest neighbor. So this, which is shown as the first row here. And then if you want to include further interaction, so you can include the second nearest neighbor. So you will have different unit cell. So this is very easy to calculate the unit cell shape and also the corresponding volume for each case. Okay, so that is the discretization being used in this method. The next is how you're going to introduce the interaction between the particles, okay? So as we talked at the background slide, we want to replace the stress divergence term in the conventional continuum mechanics with the integral term. And then as you see in the integral term is basically a force, right? You want to somehow get the force, and then the force you can understand as the interaction between a material point or particle with all the neighbors you introduced. So in order to get the interaction among the particles, then here we propose a new form of the particle potential. So as you can see here, the total particle potential is a summation of all the potential for each unit cell, okay? So depends on how many type of neighbors you introduced in the interaction, then you will have correspondingly different number of unit cells, okay? And then the potential of that specific particle is a summation of all the potential from the unit cells, basically the interaction with different type of neighbors. So as for each unit cell, the explicit form of the potential is given here at the bottom. So if you look at this, basically there are two terms, okay? The first term is kind of the classical like pairwise potential, like you have a spring, right? If you know the spring constant K, then you can easily calculate the potential of the spring on subject to certain deformation. So the first is the classical pairwise potential. And then this is also the one used in the classical lattice spring model. So besides that, so we introduced a different term, which is we kind of call it is more related to kind of multi-body, okay, interaction. So as you can see here, is rather than have a pairwise like the contribution to the total potential, we do a summation of all the bonds, like the deformation or the stretch of the bonds connected at this particle with the corresponding neighbors. We sum them together, and then we have a kind of long local contribution to this potential. So by introducing this term, it kind of very conveniently overcomes the classical issue with the lattice spring model, which is related to a kind of fixed Poisson's ratio in the conventional lattice spring model if you only consider the pairwise interaction between the particles. So we will show that numerically. Okay, so the next is now you propose some potential form, okay? But we have some parameters haven't determined yet, such as the spring constants, like you can think that as a spring constant, the K, and another parameter is related to the long local term, that is we use the T. But nonetheless, so with the potential, you can differentiate that with respect to the stretch for each bond, then you can get the interaction within that bond, right? So this is a very straightforward process that you just take the differentiation, first order differentiation, you can get the interaction force between each pair of particles. So if you look at this form of the interaction between particles, say I and J, here we use the triangular lattice to do a demonstration how the interaction force really looks like. So you can see here, the first term depends on the stretch or elongation of that bond, right? Connecting particle I and J, and then you assuming you have a constant for that, then this is purely from the deformation of that bond. We will contribute force to the bond connecting the two particles for sure. And then the second term here, this is a kind of accounts all the contributions from the neighbors. Okay, if you look at the first is from the neighbors of particle I, such as if you look in the left half of all those bonds, will contribute to the interaction of I and J. And then the second part is, the rest, the two parts on the right side is corresponding to the neighbors of particle J. So basically here, the interaction between I and J is completely non-local. It's not limited to, or not only has contribution from the bonds connecting I and J, but also has contribution from all the bonds, the neighboring bonds connected at I and J. Okay, to go back to the first question I asked is, how can we determine the model parameters, right? We introduced some new model parameters, and then how can we determine those in order, say, if we model the same problem, one, we use the continuum mechanics theory, okay, assuming no fracture, assuming just the deformation problem. On the other side, we use this LPM method to model the same problem. For sure, we should get the same material response, the same behavior, right? Because physically, they are basically the same problem, but you just use different numerical techniques to look at that problem. So then it is also based on that concept, we tried to derive the model parameters. It's basically assuming the energy in the continuum setup is the same as the energy you should get in the discrete setup, okay? So since we have the energy on both sides, so and then we just assuming the energy on both sides are equivalent, then we can build some connection of the model parameters, which is K and T here, with respect to the material properties from the classical continuum mechanics, which is just the Young's modulus and the Poisson's ratio, that those are the most frequently used for isotropic material behavior. But for anisotropic, you may have more than two, you may have some others, but the general idea is as long as you equivalent the energy, then you for sure can uniquely determine the model parameters with the material property you can have from experiments, right? So this is the relation. So assuming that, and then based on the theory of hyperelasticity, we know the rank force material stiffness tensor is just the second order derivative of the potential energy with respect to the strain tensor twice, right? So here we divided by V indicates the potential we have is actually energy, but since we need to use energy density, so that's why we need to have a V divided by here. Now, so on one side, we can express this rank 4 tensor using material properties, right? So that's unique. And then on the other side, we have this expression, the rank 4 stiffness tensor expressed in terms of the K and the T in the LPM method. Then we just component-wise make they are the same. Then we can calculate all the model parameters uniquely in terms of the material property. Here we used basic relations between the bond strain. So if you know the stretch, you know the initial length, then you can calculate bond strain, right? And then the relation of that can be connected to the strain tensor at the specific particle. So this is the relation we have used. For sure, this is only applicable to infinitesimal strain problem, okay? Now, assuming you derived your model parameter, okay, you can get the bound force under certain deformation, and then you can rewrite the equations of motion rather than using integral term for the force. Now here, since you have very limited interaction, okay, depends on how many neighbors you have, then the interaction is basically the interacting neighbor is a finite number. Rather than doing the integration, we can replace that as a summation. Okay. So this is the reformulated particle equation of motion. We don't have any spatial derivative here, so that can very good solve the problem of when you have spatial discontinuities in the conventional continuum mechanics theory. Okay, this is just to give you ideas how the parameters looks like in terms of the material property, say for isotropic linear elastic problem. So for all different lattice structures, the 5 we mentioned previously, we can derive the unique relationship between the model parameter and also the material properties. So for 2D, we have different assumptions, plane stress or plane strain for 3D. So this is all the relations we can have for isotropic material. Okay, so this slide just to briefly show how the elasticity verification result looks like. So again, here we just compare our LPM method with the conventional continuum mechanics, which we modeled here using the finite element method. So basically we have the same problem. One is we run the same problem using finite element methods. Another side, we run the same problem using this new proposed methods, and then we compare the results. So this result has already previously shown by Dr. Yang. Here we verify the Poisson's ratio effect, as I also briefly mentioned at the beginning. If we only consider the pairwise interaction between the particles, and then we will have the issue of limited or fixed Poisson's ratio. That is the case in the classical or in the conventional lattice spring method or model. So here we input Poisson ratio, and then we should expect the same output of that value, right? So that is the diagonal we should match. So we look at the 3D case here. I didn't show the 2D case, but essentially they matches very well, the same as this 3D case here. So on the right is a very simple problem. You have a 3D plate, a circular plate. You just apply a concentrated loading at the center of the plate, and then depend on the value of the loading, you will for sure have different diffraction in the transverse direction. Here we compare along a radial direction, the deformation with respect to the finite element solution. So as you can see here, on the top shows the general profile of the displacements, and on the bottom is along the radial direction pointwise comparison between 2 different methods. As you can see here, very good accuracy achieved using this new proposed LPM method. Compare the results from finite element methods. Okay, so here's now we just assure that we can model the elastic behavior of the material, right? Now, if we want to look at the ductile, like the failure of ductile material, and how can we extend this model from purely elastic problem to a elastoplastic problem? So before talking about the formulation or the extension, let me just briefly review some plasticity theory in the conventional continuum mechanics. So this only limits to the rate-independent infinitesimal strain theory. So you can have a general finite strain theory and the rate-dependent. So, but here we limit our discussion to rate-independent infinitesimal strain theory. So on the right, this figure is a very classical. You can get this from experiment, or like this is a very standard stress strain response of a typical ductile material. So if you think about you do a uniaxial tension loading, right? So at the beginning, you for sure you have elastic behavior of the material. If you release, and then the material will get back to the undeformed state. So until to certain limit, which here is a yielding point, and then the material will get into the plastic deformation. So for perfect plastic deformation, perfect plasticity, you will not have a hardening, which means the curve will become flat, pure. Okay, but in real materials, you usually have different degrees of hardening, strain hardening, right? Then that's why you will not see a purely flat curve when the material kicks into the plastic deformation. Rather, you will see a slightly kind of diverged curve here. The slope will be much smaller than the slope you have for the elastic deformation. So anyway, this is just a very standard material response behavior. So here we want to mention several different concepts. One is during the elastic, the slope of the curve will give you the Young's modulus, okay? And then during the plastic stage, you have also a same kind of similar quantity, which is called the tangent modulus, okay? So which is just if you choose a point and then you take the tangent of that point, then you can get a slope, right? So that is called the tangent modulus. And then you can also have a second modulus, which is ES indicated here. So during the elastic deformation, all these three are the same, but when you get into the plastic deformation, the value will be different depending on the location of that point. Okay, so and also for this rate independent infinitesimal strain theory, we usually assume, okay, the total strain can be additively decomposed into two parts. One is the elastic part, another is the plastic part, okay? This additive decomposition usually applies to infinitesimal strain theory. When you have finite strain, you don't do this additive decomposition, you do the multiplicative decomposition, okay? So in addition to that decomposition, we have another decomposition, which is we can, for the strain tensor, we can decompose into a deviatoric part and also a dilatation. Or sometimes you can call it like hydrostatic part and also deviatoric part. So these are the two decomposition of the strain tensors. We will kind of see the same decomposition in this LPM method. That's why I talk about those concepts here also. So the next is the constitutive behavior. So here we are assuming is, as we know, so the stress only depends on the elastic strain of the problem, right? So if you have a linear stress strain relation, which is written as here, you have a rank 4 elasticity tensor, and then you have rank 2 stress, and then the rank 4 times the rank 2 strain, elastic strain tensor will give you a rank 2 stress tensor. Or you can write in terms of the total strain tensor and use the second strain modulus, which is shown as ES, okay? So another thing I want to mention is the associative J2 plasticity theory. So we know you may have non-associative, but here we limit our discussion to associative J2. That indicates what is associative, basically that indicates if you have a flow law, you see the normal of the flow direction is determined as the derivative of the yielding function with respect to the stress, okay? So let's look at the yield function. Yield function in the J2 plasticity is very easy. So if you have this, the J2 here is the second invariant of the stress deviator, okay? So if this is the relation, as long as this quantity exceeds a yielding limit, and then the material will goes to deform plastically. And also the flow law determines how your plastic strain tensor will evolve during the loading process. So you, which is the relation is shown here, the rate of the plastic strain is equal to a gamma times the partial derivative of the yield function with respect to the stress. Okay, this gamma is sometimes you call is a scalar plastic strain. And another piece of information you will need it in terms of you may have a hardening, right? Strain hardening, because for most of the real material or real problem, you actually have the hardening. So you may have different hardening. So most common is isotropic hardening, and also you may have a kinematic, or you can have a mix of both of them. So, but anyway, so in terms of hardening, the yielding strain, the point will move, okay? Depend on different hardening rules, the determination of this yielding will be different. So we will talk about that later. So a little bit about the yielding function. So as we already know, so if the yielding function less than 0, which indicates the equivalent stress is less than the yielding stress, then the material is on the elastic deformation, right? Then the scalar plastic strain will be 0. You don't have any plastic deformation. So when the yielding function is satisfied, which means the phi is equal to 0, you have the equivalent stress is the same as the yielding stress, then your material will start to deform plastically. And then by that time, you will have 0 or greater than 0 equivalent plastic strain or scalar plastic strain. Okay, those are the concepts usually talked about when we model the isotropic or infinitesimal strain theory for the isotropic plasticity. So we now trying to formulate this same concept or equivalent concept as to those we have just discussed in this new method. Okay, so here we don't have strain, but we have a stretch within each bound, right? So, and then the bound, for sure, we can additively decompose into elastic bound stretch and also plastic bound stretch, okay? And also if you write in the incremental form, this which is shown on the bottom, you have an increment of the strain, the stretch, you can decompose the increment into elastic part and also plastic part. So if you have a summation of all the bound elongation associated with a specific material point, and then the same decomposition can be used. The summation of all the total bound stretch can be additively decomposed into elastic part and also plastic part, and then the same for the increment. Okay, this is the first concept. We kind of also additively decompose the bound stretch into two parts. So with that given, now let's look at the bound force for a single particle and its associated bounds, okay? So this is the expression we used to calculate the bound force between two particles for the isotropic material. So on the elastic deformation, it's easy. So we have all the deformation is elastic, all the bound stretch is elastic. We don't have any plastic. And then the force is basically the parameter, model parameter times the bound, total bound stretch, and also in addition to that, you have a non-local contribution here. This is only for a one contribution from one particle. See, for a bound, you have two particles. Now you have a contribution to the force within that bound from one particle. You have another particle from the other particle. But here we only look at the contribution from one particle only. And then for plastic, under plastic deformation, we can have the similar expression, but we need to update the model parameters. Initially for elastic, we use the elastic denoted by here as elastic. Now we need to update that, use a plastic model parameters, and then the same for both K and T. Okay. Then the question here is, for the elastic, it's easy. We already showed the relationship of those model parameters KE and TE in terms of the Young's modulus and the Poisson's ratio for isotropic material. So the question here is how can we get the model parameters under the plastic deformation for the KP and the TP? How we can get those? Okay. Now let's look at the review. I mean, here we just look at the simple cubic lattice as an example to look at this process. So on the left, the list expressions of the model parameters K and T in terms of Young's modulus and Poisson's ratio. Here R here is the particle size. Okay, since you started with a discretization, it's a regular discretization, then for sure you will know the radius of each particle. Okay, that is a parameter you already know before you start doing your discretization using this method. So on the left is the expression of the model parameters based on the material properties for an elastic problem, okay? On the right, this is the same, we use the same expression, but we need to update correspondingly for the, like say, if you initially used the Young's modulus and the Poisson's ratio, and then we just need to update for the plastic deformation correspondingly, we use the tangent modulus for the plastic deformation and also the corresponding Poisson's ratio for the plastic deformation. So how can we get those? So as we showed here in this figure, so this is a simplified bilinear material response curve. So the first part is elastic, the second part is plastic. We have both tangent modulus, right? Then for the plastic deformation, we just plug in the tangent modulus to calculate the corresponding material or the model parameter K during a plastic deformation. Then the question left is how we can get the Poisson's ratio for the plastic deformation. Okay, this is a calculation of that. So basically here you have two limits. We know on the plastic deformation, since the material is incompressible, okay, that is to say the Poisson's ratio is 0.5 for material on the purely plastic deformation, okay? And then another side is you have an elastic, right? That is the Poisson's ratio you know for material on the elastic deformation. Basically you have two limits value for the Poisson's ratio for material under the mixed of an elastoplastic deformation. One is the pure elastic, another is pure plastic. Then you can interpret those two values to get a value where you will have a mixed deformation of elastic and the plastic, right? This is the relation we used. The V here, the nu here is the elastic Poisson's ratio, and 0.5 is the purely plastic deformation, the Poisson's ratio for purely plastic deformation. And then we use the tangent modulus for pure elastic and also elastoplastic, that is E and EP, to interpret those values to get a value when you have a mixed deformation. Now you know the EP and the VP, then we can easily get the KP and the TP. And then if you plug that back, then we can easily get the force increment for material on the plastic deformation. So then next is, since we now can calculate the force of a bond on the elastoplastic deformation, the next is like how should we determine when the bond is actually going to a plastic deformation, right? Here we use an equivalent maximum distortion energy criteria. So, and also a non-local yielding criteria we propose here. We based on the energy density, the maximum distortion energy density, rather than the stress, like the in engineering, we may just express the J2 plasticity using the stress components, right? Rather than really looking at the maximum distortion energy density to check whether the material point is yield or not. Okay, so this is the form of the energy decomposition. Okay, we can decompose that into an energy part purely related to distortion, deformation. Another is purely dilatation. Okay, this is kind of very similar to the additive strain decomposition. Okay, but limitation of this decomposition is only applied to isotropic material. Okay, for anisotropic material, this decomposition may not exist. So, and also since we only talk about isotropic plasticity, so we use of this assumption should be fine here. And then the question is, how can we calculate the distortion energy portion from the total energy you have for a system, right? For a particle, say. So we just need to calculate that, and only that part will contribute to the yielding of material. We know the yielding the critical distortion energy density from experiments that is equivalent to the sigma y, the yielding stress you can get from experiments. Okay, here, this is how we get the distortion energy. So here we just use the distortion part of the bond and also for both terms, and then we can get the distortion energy, right? Since we not using any other non-distortional components of the elongation in this energy calculation, we only use the distortion part, and then we should get the distortion energy easily. So for this term, if we look at the second, for this energy, if we look at the second term here, so since here we have a summation of this, due to we already know plastic incompressibility, right? The volume change during plastic deformation is basically 0. Then here is basically, this is the corresponding volume change for the plastic deformation. Then you will have 0 here for this summation term. That's to say you will have the second energy term goes to 0 due to the plastic incompressibility. Now you only have the first term. And then how you get the dilatation part of the elongation of a bond. So which is right here. So the average dilatation part of all the bond stretch associated with a particle is just the average of the summation of all the stretch of the bonds connected at the particle divided by the number of bonds you have. So that will give you the dilatation of each average dilatation for a material point. If you know the average dilatation, and then you can just subtract that from the total elongation, you can get distortion part. The same if you write in the incremental form. Now with that known, then you can easily calculate the incremental distortion energy, right? So with the known distortion part of the increments of a bound stretch. So a material is under plastic yielding if, so this is the yielding criteria. If the maximum distortion energy density is equal to the one you get from experiments, and then the material is undergoes yielding, okay? And then this is the relation express the maximum distortion energy in terms of the yielding stress. The mu here is the second Lamarck's constant. Okay, here next is now we can use the criteria to determine when a bond goes to yield or not. Then like next step is to determine what is the plastic strain, right? That is the flow rule. Should each bond have under a certain loading as if the bond is undergoes plastic deformation. So recall the two forms of the incremental force calculation, right? We showed at the beginning, we have these two forms. If we have material is purely elastic, then we use this form to calculate the force increment in the bond, right? And then if the material is elastoplastic, then we use this second expression to calculate the force increment, okay? Now, so again, if we use the plastic incompressibility, that is the summation of the increments for the plastic part of all the stretch, then should be equal to 0. If we plug this in, then we, under plastic deformation, we have the summation of the all bond stretch associated with the particle. It should be the same as summation of the total elastic stretch, okay? Since you have the plastic incompressibility, the summation of all the plastic should equal to 0. Then you will have this equivalent between these two. Now, so if you plug in this back into this equation, so no matter which way you choose to calculate the force increment, these two equations should be the same. Then you can get the elastic stretch. It's basically by equating these two, and then you use this relation, the summation of all the bound stretch is equal to the summation of the elastic part. Then you can rearrange the terms, you will get the elastic bound stretch, which is given here. So you will need the model parameters KE, TE, and the TP and the KP in this formulation. Now, as long as you have the elastic part, so we know the total elongation, and then since we assume the additive decomposition, right, then we can get the plastic part very easily by subtract the elastic part from the total. Then you can get the elastic bound stretch during each loading step. So here we only have a scalar plastic stretch. We don't have the, the direction is explicitly already given. It should be along the bound direction, right? If you have bound in horizontal direction, then the deformation plus deformation of that bound should only goes to aligns in the horizontal direction. Okay, that's why here we kind of just like one-dimensional flow rule. We don't have, it only can go like to the left direction, to the negative, or to the positive, to the right direction, right? You can only have these two directions, which is slightly different from what we have in the classical continuum mechanics, which is you need to take derivative. In the case of associative flow rule, is you take the derivative of the yielding function, yielding surface with respect to the stress, right? You can get then which direction this plastic strain will flow. But here, since we only have a 1B, then it's just either go in the stretch direction or in the compression direction. Okay, so the last piece of this equivalent J2 plasticity theory for this LPM is the strain hardening. As I said at the beginning, so usually we observe different types of hardening or different levels of hardening of the real material in the experiments or in the real application. So as I said, this can basically categorize into three groups. One is the isotropic hardening. Okay, isotropic hardening here is shown on the right using a figure. So so the sigma y1 is assumed is maybe the initial yielding point. Okay, if you continues to loading, continues to exit more loading on the specimen, then the material will continues to yield. Okay, and then the yielding point will move like isotropically, expanding the circle. Here, this is plot in the sigma and also the second invariant of the stress deviate that space. Okay, so you will see the yielding surface will isotropically expand. Okay, that is called isotropic hardening. But when you look at the kinematic hardening, you see the size of the surface is not changing, but the center of the yielding surface is moving, okay, which is different from the isotropic case. Initially, you might have the center is at the origin of this space, okay. It can move depending on the actual loading of the problem you are looking at. So this is the two different types of hardening here. So for the first one, it's easy. We just need to keep track of the point where you started to unloading, okay? If you start to unloading, then that unloading point will become the new yielding point. If you, assuming you're going to reload again, okay? So that is the new yielding point. We just need to keep track what is the corresponding bound stretch for when you start to unload your specimen. So for the kinematic is the same. We also need to check that, but in addition to that, we need to have a back stress. So back stretch. So here, this is very similar concept to the back stress we have in the classical continuum mechanics. So since you just need to translate, okay, that's why you have a back stress. This will translate the yielding surface. And the mixed is just a mix of these two. So we introduce a different alpha parameter. If you choose alpha equal to 0, then it goes to isotropic. If alpha equals to 1, then this will give you the kinematic hardening. So if you have an alpha value between 0 and 1, then basically you have mixed isotropic kinematic hardening. Okay, so we have all the ingredients we needed to model elastoplastic material using this new method. So let's look at some numerical examples here. So this one shows the, we did a very simple first verification is a beam under uniaxial tension. So you have this beam, you fix the top and then you apply some loading, pulling the bar, okay? This is the material property given for this problem. So the first loading case is just a monotonic uniaxial loading, okay? And then we compare different quantities. And then we look at the prediction with the theoretical results. And then we see a good match. So the second case, we have some unloading, but the unloading is not to the reverse plastic deformation point. And then we start to reload again, which is showing this curve. We initially load and then we unload and then we reload again, okay? So which is showing here the plots in terms of the material response. The prediction matches well with the theoretical value. So now here if you don't have reverse plastic deformation, then the hardening will not make any difference here, okay? So, but if you have the reverse plastic deformation, which is demonstrated here using uniaxial cyclic loading, okay? We have initial loading and then we unload to the reverse yielding point and then we further continue the unloading and then we just reload again. So we have both loading plus deformation and unloading, reverse loading plus deformation. So in this cyclic loading cases here, we look at the both isotropic hardening and the kinematic hardening and the mix of these two. So we see the prediction matches quite well with the theoretical curve we have here. So this example just show to match the surface, the yielding surface. So we do a biaxial loading of this block. So this is the setup. So we have if we use J2 plasticity, we have a yielding surface. We can easily plot the yielding surface by the value of these two stress. And then we just plot our predict the yielding point, and then to check whether that yield surface is the same as you have from the theoretical values. So you see matches very well with the theoretical value. So we also compared it with the plastic deformation. So the plastic zone. So you see on the top is the prediction using this method. On the bottom is finite element, but here we used a slightly different geometry. We introduce a hole at the center of the beam. The loading is the same. We can see the plastic zone matches well on the different loading values, matches well with the finite element solution. So this is the displacement field. So we plot the displacement field again with the finite element solution. So this is, we did a little bit more detailed study of this problem. We look at the shape of the hole under the different kinematic, on the different strain hardening. So how the shape deforms, right? So, and also how the curves looks like. So you see here, this is the red curve is the initial shape of the circle of the hole. If you you stretch that direction, and then you will have a plastic deformation, and then this is a permanent, and then you have unloading. So you will see after you unloading, so the hole is actually becomes the shape will becomes different than the initial shape because you have permanent deformation, the plastic deformation there. Okay, with that, I'd like to conclude. So basically the work you presented here can be found in these two papers. So, and also about ongoing work. So we are working on extending this approach to look at the crystal elasticity. That is mainly for the failure of brittle materials. So say if you have a ceramic material, you want to model the physical behavior or the mechanical behavior of this material, and then we can use this crystal elasticity based failure modeling capability. So, but the most of the case, the material is maybe like for the metal alloys is actually a ductile material. Then we may more interested in the crystal plasticity deformation of this material, and then also the failure of the ductile or the ductile failure regime of this material. So we are working on those areas. So with that, really appreciate your attention, and thanks to listen to me. And I am open to any questions if you may have.
Thank you, Hailong.